Okay, so I have put up problem set 7, which is about cooking, and therefore the movement of heat and things to do with water, steam, and ice, which I'll come to hopefully later today. I hope I haven't made any mistakes with setting it up. I've got the deadline set correctly, I believe, and so on. If you ever see a mistake in the problem set or in how it's the deadlines, things like that, tell me about it. I'll fix it. All right, so where we left off last time was in dealing with the movement of heat from a hot wood stove into the room. And as I told you last time, heat flows. Heat is thermal energy on the move. It is flowing from a hotter object to a colder object. The objects have the same temperature, doesn't flow at all, and we'll come to that when we talk about the laws of thermodynamics. But for now, it's just heat's flowing from the hottest object in the room, namely the wood stove, to the rest of the room, and it goes by the 3 famous mechanisms of, or infamous, whatever, mechanisms of heat transfer: conduction, convection, radiation. And I started with conduction. Just to remind you, the story of conduction is the movement of heat through a material without the material itself actually moving. So fluids can conduct heat, but their tendency to move introduces a different way in which they carry heat, which is convection. But mostly with conduction, we're thinking of solids like a block of wood, a block of metal, a block of cement, a block of glass. The heat goes from the hotter side to the colder side, and it goes via 2 main processes. One is the jiggling of atoms and molecules that are adjacent to one another. And statistically, if you've got a lot of thermal motion over on one side, which corresponds to high temperature, and you've got, let me pick an object, this stick again. So you've got a lot, this is hot, it's got a lot of thermal motion over on this side, and on the side that's cold, the thermal motion is less. It's just statistically likely that these fast-moving jiggly guys over here will bump the ones next to them and do more work on them than they do work on back. So thermal energy statistically wanders from the hottest part to the cooler parts and cooler, all the way over to the coldest. Is that okay? That is a slow process typically, which is why the thermal conductivity of things like a piece of wood are not all that good. It takes a long time for the heat the amount of heat flow is modest in most cases. I should point out, though, that things like the rate at which heat flows via this mechanism and the other one that I'll mention in a moment is related to a couple of things. First off, how far apart the hot and cold regions are. The farther they are apart, not surprisingly, the slower the movement of heat through the system is. Another thing that matters is how big the temperature difference is. So if there's a very small temperature difference, this is a little hotter than that side, again, the flow is relatively small. The flow is measured in units of heat, which is units of energy, per second. So it's a flow of power. It's thermal power that's moving through the stick. If the temperature difference is small, the thermal power flow is small. The third thing that matters is the cross-sectional area of what's carrying the heat. So if it's a stick like this, there's not a lot of cross-sectional area. You slice it off like sausage slices, and they're little. So there's not a lot of path for the heat to flow through. So basically, in general, if you want a lot of heat flow, you want, first off, you want a material that carries heat well, which is we'll come to. Second off, you want a big temperature difference between hot and cold. And third, you want the distance that the heat has to flow to be small. And lastly, you want a big cross-sectional area for which, a big highway for the heat to flow. So it all makes pretty good intuitive sense if you think about it, how you get a lot of heat flow. We'll see later on when I talk about clothing and insulation and stuff, if you want to have minimal heat flow, you want small temperature differences, you want big separations, you want small pathways. Pretty straightforward. And then rotten conductors of thermal energy. Okay? Okay, so wood carries heat by this bucket brigade process of jostling atoms and molecules. Metals have a second possibility. Metals, because they have electrons that can move long distances, have the possibility of conveying heat through those mobile electrons. And they're very good at it. They carry heat long distances because they don't have to sort of stop atom by atom by atom. They can fly through long distances in the metal and pick up heat at the hot end and go a long distance and drop it off at the cold end. They don't go the whole length of a metal. I mean, people do work on trying to make materials that have very long path lengths for their electrons. But in general, you don't get vast travel. You get modest travel. And the more disrupted the metal is locally, the worse this mechanism is. So a metal like stainless steel is not a good conductor of heat because it's an alloy with all kinds of, it's got at least 3 metals in it: iron, chromium, and nickel. And it's structurally kind of nasty for the electrons. They just don't manage to go very far before they hit something. So they can't carry heat the way they like to. So stainless steel, you'll deal with this in the problem set. Stainless steel is nice for keeping things clean, but it's not very good for carrying heat. So when you build cookware out of stainless steel, you have to use it carefully. Otherwise, you end up with cookware that scorches your food. Very thin-walled pots, for example, made of stainless steel. You can heat one side red hot and the other side still cold. So you put your food in there, you scorch one side, you don't cook the other side. This happens on electric burners where you have the spiral, that hot spiral that tries to heat the pot. You can actually see the spiral through a thin-walled stainless steel. The spiral's glowing red hot. You can see the stainless steel start glowing red hot in the spiral shape through a really cheap stainless steel pot. Okay? The good conductors of heat are the good conductors of electricity. Copper and aluminum are the best choices. Silver would be great, but it's expensive. All right? So for a wood stove, what's the issue of conduction in a wood stove? You've got the fire going on inside the stove. You want to get heat to the outside of the stove where it can start going into the room. It goes through the walls of the stove by conduction. And because the walls of the stove are pretty thin, and there's a lot of surface area, and the temperature difference between inside and outside is initially quite large, the flow of heat through the walls of the wood stove is very fast. Lots of heat goes through there. There's a question that's coming up here, which I can ask it. I'll ask it just to give you something to do. In which direction does heat more heat flow for a given difference in temperatures? And that is through the wall of the wood stove from inside to outside, or along the wall of the wood stove from one side of the wood stove to the other. And the wall of the wood stove is presumably fairly thin. So which way does heat flow faster? Do you understand the question, or questions on the question? How many think that heat flows more readily through the thin wall of the wood stove from inside to outside? How about along the wall of the wood stove from one side to the other? How about they're both equal? Okay, so the vast majority of the voters who will stick with their votes are going for A, which is the right answer. You saw me actually last time. I had a thin wall I had a piece of stainless steel that was a tube. It had a fairly thin wall. And I could heat one side red hot while holding the other side a few inches away. And that's because the heat flow along that very thin piece of metal with some distance to it is very weak. The flow through the wall, because it's a big surface when you're going through a wall, and the distance between the hot and the cold is very small. The heat flows through pretty well, even in stainless steel. So what is this useful for? Well, it's useful, again, going back to stainless steel pots. If you've got a stainless steel pot, a cheap, really thin stainless steel pot, the heat will flow through it from the outside to inside quite nicely. But heat will not flow along it from one part of the pot to the other part of the pot through that very thin wall. There's just not enough meat there, and the separations are too big. So the heat flow is terrible, and that's why you end up with weird things like you get a red hot spot inside the pot, and you have somewhere farther away down the pot, it's cold. It's not heating at all. Okay? Any thoughts about conduction, questions? I've already showed you all my demonstrations for, well, worthwhile ones for conduction. Then convection. What convection is the movement of heat in a mobile fluid. So if you're going to let the material itself move, it can carry heat, in fact, as its own thermal energy. So you put heat into water, for example, so you make hot water, and then the hot water moves for some reason over to here and into a cold region and distributes its thermal energy there. That's movement of heat by way of conduction. Convection, sorry. Okay, I can show you convection. I'm going to blank off that screen. Why is this? I can't blank off the screen. I'm sorry, I was trying to. It's misbehaving. I can turn the projector off. Maybe. It's too dangerous. I don't know which one's which. There we go. All right. Yeah. Come on. Come on. It's crazy. That'll do. All right. What I wanted to do is, what you're seeing here now, I finally got this thing to work. We've got an old-fashioned light slide projector sending light through a container of water that you can't see. It's here behind a lens. And then we're projecting an image of that container of water up onto the screen. And this coil here is a coil of wire, of heating wire, and we're going to run electricity through it so it becomes hot. And it's going to heat the local water up, and you'll have a little bit of hot water in the middle of cold water. Well, as with hot air, heated water rises. It becomes buoyant within the cold water, and it will float upward. So can you see the little streamers of heated water rising up to the surface? So they're carried up by buoyancy. The stuff we study in the context of balloons is carrying it upward. And if you put your finger in that stream of water, it's going to be hotter than the rest of the water, because it literally is hot water. It goes up, and you can actually see the whole pattern. It goes up, and it spreads out up here near the ceiling of the water. This is as high as the water can go without sort of bumping into the air, and it will not go higher than that. So it spreads out on the ceiling, and if you could see it, you might, you might see that it's descending out here to make up for the water that's rising. The water that's heading up has to be replaced by something. So water is flowing back into this heating wire and rising up. And we're getting what are known as convection cells, where the heated fluid rises up, carried by natural buoyancy, spreads out, descends, and then returns to pick up more heat. So it's a steady transfer of heat from the hotter parts to the cooler parts of the environment. And this is exactly what happens with a wood stove. A little harder to see, not altogether hard to see, but near that wood stove, it's heating the local air, which rises, carried by natural buoyancy. It's at atmospheric pressure, but it's hot, so it must have a low density. So its density is less than the density of the surrounding cold air, and up it goes. It's pushed up harder than its own weight, and it floats. So it goes up to the ceiling, spreads out on the ceiling as hot air, and eventually, after transferring a lot of its heat to whatever it touches up there, it cools enough to descend and go back to pick up more heat. Is that okay? And I just want to let the lamp cool down. I can put that. Should I even try this? I'll put this back, maybe. Yeah. With a wood stove, a substantial amount of its thermal energy is moving into the room by way of convection. It heats all the air around it. That air rises up, spreads out on the ceiling, and by the time it comes back down, it's cooler. So, I mean, where do you want to be if you're really going to want to be seriously warmed by a wood stove? You want to be above it, which is an awkward place to be. So wood stoves are great at warming the ceiling by way of convection. And if you've got a very tall room, so you put it in the middle of an atrium room with a two-story room or something like that, a lot of the thermal energy is going to go up to the second floor. So what can you do? Well, the convection that I've just described is natural convection. Just to put a word in front of it, it's convection associated with the natural buoyant effects, the flow of air driven by temperature. If you want to have that nice warm air come down to where you normally live, put a fan up there. So wood stoves and ceiling fans are a natural pairing. You put a fan up there at the ceiling where it can get in this nice warm air and have it blow that air downward. So you can run the ceiling fans both directions. You can have them push air up or push air down. You may well, in this case, want to push the air down. So it floats up, goes to the ceiling fan, and gets blown down toward the ground to where people are. When you're doing that, you're still transferring heat by way of convection, but that's known as forced convection. You're not waiting for natural buoyancy to do the job. You're doing it deliberately. All right? And sort of as my public service announcement asides, many modern stoves or ovens are convection ovens. And as you'll see in the problem set, all stoves are convection ovens. Natural convection occurs in any oven, depending a little bit on how you do the heating, as again you'll see in the problem set. What the convection ovens do is they stir the air deliberately with a fan. So that's really forced convection. So if you wanted to name the convection ovens sort of more properly, they would be called forced convection ovens. Because you turn the fan on, now you're not waiting for buoyancy. You're just stirring the air vigorously the whole time. And it's much better at making sure that all the cookie sheets, all of them get hot air coming by. You don't wait for it to just wander up because of natural buoyancy and miss some of your cookies. All right? So having told you about this, how about this possibility? If you heat the top of a fluid, for example, water, will natural convection carry heat to the bottom of that fluid? You okay with the question? How many think that yes, it will carry heat to convection? Natural convection will carry heat to the bottom of the fluid. How about no, it won't carry heat to the bottom of the fluid? Okay, so the majority are going for no. Let me see whether I can, this is where I want to do it. Yeah, I will zoom in on. So what I've got here is a test tube of water filled up to there. It's cold water, it's just out of the tap. And I'm going to heat it, not at the bottom. If I do this, I'm going to burn my hands very soon. But I can do this. So I'm holding the bottom of the test tube. Glass, since it's not an electrical conductor, is not a very good conductor of heat. I will make the top of the test tube quite hot, but heat is flowing very slowly down the glass of the test tube to my hand because it's just not, it's not a good conductor. If it were copper, I'd be burning my fingers, but it's not. And water is also not a very good conductor of heat. So if you hold the water still and make one part of the water hot and one part cold, the heat slowly works its way through the water by conduction, but it's kind of a crummy process, very slow. And I now have the water boiling. Can you see that it's boiling? So I've got boiling water at the top of the test tube. And it's not boiling as vigorously as I would expect, which is okay, because usually it squirts all over the place and rolls down the outside of the test tube to my fingers and burns me anyway. So I've got boiling water 4 inches from my fingers, and I can't feel any increase in temperature down there. So the answer to the question, going to go back to the question that's up here, is if you heat the top of a fluid, natural buoyancy does not carry heat to the bottom of the fluid. The only thing that's carrying heat to the bottom of the fluid here is conduction, and it's terrible. You okay with the idea that there's no convection coming down? And that it's conduction that is carrying heat down? What little it's coming down? Okay, I can stop. I know better than to touch the top, because it really is hot water up there and hot glass, and I will regret it. All right. So that's the story of convection. The heat rising off the wood stove, spreading out in the ceiling, possibly pushed down by a fan. That brings us to the third mechanism for heat transfer, the one that's by far the more mysterious of the bunch. And that's thermal radiation. And just as background, thermal radiation includes the entire spectrum of electromagnetic waves. And electromagnetic waves, it's more a topic for the spring version of this course, but it includes visible light. It also includes ultraviolet light, X-rays, gamma rays. These are all heading off towards higher frequencies and shorter wavelengths, which is a detail that we'll not have to worry too much about. And then on the longer wavelength, lower frequency side, it goes off into infrared light and then into microwaves and finally radio waves. But that whole spectrum of electromagnetic waves, it's all the same phenomena, it just differs in the specifics, is available to thermal radiation. And those waves, which can move, can pick up thermal energy from a hot object and carry it over to a cold object and drop it off. And the issues involved are going to be how big the temperature difference is between the two of them, how good the materials, the surfaces that are emitting or receiving these thermal radiation waves, how good they are at interacting with electromagnetic waves. Not all surfaces are good at interacting with electromagnetic waves. For example, surfaces that are shiny or that are white or that are transparent, these are all surfaces that are not very good at playing with light and light's friends, or relatives rather. So we'll look through this a little bit. First off, I should say that all surfaces that have any temperature above absolute zero, which is all surfaces, they all emit some amount of thermal radiation. And the thermal radiation depends on primarily two things. One is their temperature, and the other is how good they are at interacting with light. And at low temperatures, the thermal radiation that the surface produces itself consists of long wavelength waves, low frequency waves, and these are things like radio waves, microwaves, infrared light, and maybe slightly into the visible range. At high temperatures, we know what's high temperature, the temperature of an incandescent light bulb filament or a candle flame or the sun. Once you get up into those temperatures, the surfaces emit electromagnetic waves that are extensively in the visible, maybe even beyond the visible into the ultraviolet and off into the X-rays. So as the temperature of a surface increases from bitter cold up to heading towards the temperature of the sun, the surfaces emit different spectra of thermal radiation, starting way off into the long wavelengths. I don't know to what extent you've ever encountered the idea of wavelengths and frequencies, but the radio waves have very long wavelengths, meaning that if you take the electromagnetic wave, which itself is kind of a mysterious concept, and you take a snap photograph of it as it's going by, and you measure the distance from what is effectively a crest to another crest, they're very far apart, those crests, tens of meters apart. Something bigger. On the small end, they're about what I can reach with my hands. Wi-Fi is getting a little close. The Wi-Fi operates somewhere around here, in the crest-to-crest distances like that. But all the transmitted radio waves, the broadcast, AM and FM radio, I can't reach them with my hands. So those are long wavelengths. Those are what is emitted by very cold objects, preferentially. But as the objects get hotter and hotter, the distance between crests gets closer and closer. And for people in this room, we're emitting thermal radiation, believe it or not. It consists of waves with crests that are separated by, they're a couple of microns. A micron, so let's see, a human hair is probably about 25 microns across. So the wavelengths are, you can fit a couple of crests across a human hair, but that's still relatively long wavelength for light. We can't see it with our eyes. To see the thermal radiation that we can see has to be coming from surfaces that are hotter than 500 degrees Celsius, or what is that about? That's about 800 degrees Fahrenheit. Once you get hotter than that, you can start to see it. The thermal radiation becomes visible, includes visible light. It starts in the deep red and works its way into the oranges and the yellows, and finally up towards, it's a mix of colors, so it works its way towards pink into red. It isn't even pink. It works its way ultimately to white, and then even beyond white into blue-white, if you get really hot, hotter than the sun. So this is just a brief exploration of the thermal radiation that comes off surfaces shifts to higher and to shorter and shorter wavelengths as the surface gets hotter. We can't see the thermal radiation for things that are colder than about 500 Celsius, about 800 or 900 Fahrenheit. But once they get hotter than that, we can start to see it. It starts as a dim glow that you can't even identify as a color yet. When they first get hot enough to see them, you can see them with your night vision. And then you start to see them with your color vision, which includes the notion that it's red. And then it works its way to deeper into the rainbow. It's not rainbow spectra because it's a mixture. Rainbow spectra is specific wavelengths. This is a mixture of wavelengths, and therefore it's got a kind of a pastel character to it. Is that okay? Or questions about wavelength issues? And so the point is, the hotter the object is, the shorter the wavelength of radiation it emits, and also the brighter it gets. So the more power is coming off its surface. So that's the first issue, is its temperature. The other issue is how good it is at interacting with light at all. And there are certain materials that are terrible at emitting light. Shiny metals, like gold. True white is also crummy at emitting thermal radiation. True white, the difference between shiny and white is minimal. What a shiny surface does is it reflects, let's say it's perfectly shiny. It's ideally shiny. It takes all the light that hits it and it reflects it. And it remembers which direction the light wave came from, and it reflects it at a specific angle off its surface that depends on the angle coming in. And it's associated with mirrors. You've seen these angles all your life without naming them. But it's called a specular reflection. Bing, bing. And so if you shine a beam of light in on this shiny surface, you get a beam of light off. That's shiny. White is also very good at reflecting light. Light comes in, in principle, perfect white. Every bit of light that comes in goes back out. What changes, though, is the white helps, the light forgets where it came from. So the light comes in from this angle and it goes out at any angle. They're all equally good. So now you send a beam of light into a white surface, and instead of coming out as a beam of light as it would off a shiny surface, it comes out in all directions. So you can't see what the light source looked like anymore. But there's otherwise very little distinction between shiny and white. They're great at bouncing light off. They're consequently terrible at absorbing it. And they're also terrible at emitting it. So white surfaces and shiny surfaces are in principle unable to emit thermal radiation. So they can become quite hot, but you can't see it. Even gadgets that can see light we can't see with our eyes can't see it. Is that okay? It's a concept? The other possibility is transparent. If the surface just lets light go right through, out the other side, again, it doesn't actually absorb any of the light that hit it. It just, in principle, the light goes right on through, and it's terrible at absorbing light, therefore it's terrible at emitting it. And you may have noticed this with, for example, glass. If you heat glass up, you can heat glass really hot. Glass blowers and people who make glass art know this. You can heat it very hot, so hot that if it were most materials, it would be glowing red hot. The glass doesn't glow red hot. It's terrible at emitting thermal radiation in the visible, and therefore you don't see it. You touch it anyway, and it's hot. You know, it's dangerous for that very reason. I've certainly burned my hands on hot glass before. Okay? So the materials that are essentially unable to deal with light, white, shiny, and transparent, don't do a good job of emitting or absorbing thermal radiation. What's the alternative? The alternative is a black surface is ideally, what's black? A black surface is one that absorbs all the light that hits it. The light goes in, becomes thermal energy. And a surface that's black is extremely good at playing with light and light's relatives. So it's very good at absorbing thermal energy. It is also, consequently, very good at emitting its own thermal radiation. So black objects emit thermal radiation beautifully. Shiny, white, and transparent do not. All right? So having talked about all this, let me show you thermal radiation. You actually are used to seeing thermal radiation from the sun. I mean, the sun itself. You know, what's sunlight? Sunlight is the thermal radiation of a very hot object 93 million miles away. That surface that we're seeing of the sun, you probably have heard the temperature of the sun can be, you know, variously reported as like 100 million degrees and stuff. Well, yeah, well, that's in the core of the sun. At the surface of the sun, it's not that hot. It's a balmy about 11,000 degrees Fahrenheit, but just short of 6,000 degrees Celsius, 5,500 degrees Celsius, something like that. So the light we're seeing is coming from the outside of the sun, not the center, where it's crazy hot. It's that outer surface, and we're seeing the thermal radiation from a surface that's that's 5 to 6,000 degrees Celsius. It is incidentally jet black. What does that mean? If you shine a flashlight at the sun, the light goes into the sun. It never, it absorbs all of it. So the sun's surface is perfect at absorbing light. It is also consequently perfect at emitting its own thermal radiation. It does a great job of it, and that's what we see. Here on Earth, it's hard to get things that hot, or at least they don't hold together if you make them that hot. They're all gases and stuff, so it's hopeless. So things like the incandescent light bulbs and candles and so on, they're all somewhat cooler than the sun, and they therefore emit a different spectrum of light. They emit light more in the redder end of the spectrum. Longer wavelengths correspond to the red end of the spectrum, and so we see them as red or orange light. And if you get colder still, then it goes down into deep red and finally into, you can barely see it's doing anything, and then finally you can't see it at all. So I have up here, how to do this. Let me do first, well, first I'll work with thermal radiation you can see. And what I'm going to do is I've got two reflectors here and a light bulb over here in this one. If you can't see the light bulb directly, it's right here. It's a 1,000 watt light bulb. So it's from old projector technology. It emits an enormous amount of thermal radiation. We run electricity through it. It's going to get hot. Not as hot as the sun, but hot enough that it will look in the red-white spectral range. It looks sort of orangey white. You're used to it. It's dazzlingly bright. Sorry about that, but that's life. We're going to collect the thermal radiation that comes from it, which includes a lot of light you can't see, infrared light. So that's going to come off into this reflector. The reflector, like shiny surfaces, is terrible at absorbing thermal radiation or emitting its own, so it just bounces. Off it goes. It goes across the room into that reflector where it will be focused down by the curvature of the reflector on a match. And so you get to watch the match. Here we go. One. There's the match. And so we can light a match at a distance. Ready? Get set. So this is heat traveling as thermal radiation from a very hot filament of a light bulb to what used to be a room temperature match. And ta-da. Yes. Sometimes I've roasted marshmallows, this same demonstration. It does a perfectly good job of roasting marshmallows, except what color is a marshmallow? White. It's terrible at absorbing visible light and even near infrared light. And as a result, it's really hard to roast this way. So we had to spray paint them black. so a licorice marshmallow would toast just nicely. All right? So that's one thing to show you. The other thing to show you is, let me come back out here. This box here is just it's a metal cube. It's got a light bulb inside, an old-fashioned incandescent light bulb, as its source of thermal energy. And it's now hot, and I can actually find out what temperature it is. I thought I had a whole fleet of these little guys, but this is the only one I could find. This is a device that reads temperature by looking at thermal radiation coming off of things. And if you've ever gone to a doctor's office and they stuck something in your ear and went, temperature's fine, is this familiar? They're looking, what are they doing? They're looking at thermal radiation coming out of your ear to see what temperature deep in your ear is. And this thing, similarly, can look at whatever surface you shine it at, and it will tell you what the temperature is. Actually, after I'm done, you send it all. I just want to see what the temperature of this is. 180 degrees. So you can point this at each other and press the button, and it will read the temperature of the surface it's looking at. And just as a public service announcement, these things are really handy. I mean, it's not super duper accurate, but it's pretty good and very fast. And you can just look at hot things, cold things, because they all emit thermal radiation. So what this is, so that's that. This is an equivalent device, same device in concept. It's looking at the temperature of this box and reporting it on that bar graph over there. And right now it's saying very hot. And what it's looking at actually is a black surface. See the black surface? If I rotate this box so that it doesn't see the black surface, but instead the shiny surface, oh, prove me wrong. There we go. It's cooling off, but it still says that's pretty hot. I'll give it more distance here. So, the farther you get away from a hot object, the less of its thermal radiation hits you. So the shiny surface, as promised, there's the shiny surface, right? Doesn't emit thermal radiation very well. The black surface, great. There's also a sanded metal surface. Where is it? This I think is the sanded metal. So it's shiny, but it's not smooth shiny. So it's kind of into the white range. Very good at reflecting thermal radiation. So it's also similarly very bad at emitting thermal radiation. So the point of what I've showed you so far is, as promised, black objects are very good at absorbing light. They're also very good at emitting light by virtue of their own thermal energy. Shiny surfaces and matte shiny surfaces are terrible at emitting thermal radiation. So far, so good? How about the white surface? This actually has a white surface. You're looking at it right there. And that white surface, according to everything I've said, should be terrible at emitting thermal radiation. And so let's try it. Dun, dun, dun. Oh no! It's pretty good at emitting thermal radiation. Who knew? So here's the story. Do you understand the problem? Are you okay with the problem? Black, as billed, emits thermal radiation, great. Shiny, dull, matte shiny, emits poorly. White is supposed to emit poorly also. but something's wrong here. What's wrong here is this. We all see with our eyes, we see what's only a small portion of the electromagnetic spectrum, the visible spectrum, right? We see from the deep red into the far violet, and that's it. We can't tell what's going on outside those with our eyes. There are animals that can. Some animals see farther into the ultraviolet than we do. Some of them see deeper into the infrared than we do. The thermal radiation associated with objects in this room, at the, room temperature, at human body temperature, at the 200, what did I say, 200 degrees of this box, all those surfaces, they're emitting thermal radiation, but it's relatively long wavelength thermal radiation that we cannot see with our eyes. We can see it with devices, but we can't see it with eyes. And we can't tell what color that white surface is except in the visible. When you look at the visible, it's white, this sheet of paper. This is white in the visible. If some alien visited and the alien has eyes that were designed to see in the infrared, all across the infrared, and could not see visible light at all, you might think they would look at this and in their own way would say that that's white also. But they wouldn't. They would say it's kind of gray and maybe even into the black. Why is this? It turns out that surfaces of most things, except for the metals, regardless of what color they are in the visible, they are black in the infrared. If you go near visible, life's complicated, but deep enough in the infrared, they're all black. Virtually everything in this room, if we could see in the infrared and only in the infrared, everything in this room would be black except for these shiny mirrors would be shiny still, a few other things. Are you okay with the idea that the color depends on what wavelengths you see? So that it turns out most things in the world are black in the infrared. It's a great equalizer. We're all, all this focus on skin color, we're all black in the infrared. And that's part of the reason why this gadget, what I hope is floating around somewhere, when it looks at things, it is assuming that everything it's looking at is approximately black in the temperature range of room temperature thermal radiation. So it will read accurately on almost everything in this room, except for it will not be able to read the temperature of those shiny mirrors because it will simply read the reflections coming off those mirrors. Window glass, it turns out, is black in the infrared also. So it's not transparent. It's black. So if you go and try to measure the great outdoors through a window, you will see the thermal radiation not of the outdoors, but from the window. Yeah, Betty. Oh, you see your reflection. Yeah. So if you look at glass has an interesting property that it has a reflection. It has a 4% reflection coming off of it. And so in the infrared, it's probably similar. If you take a thermal camera, so she's talking, if you take a thermal camera, which not only does it see the temperature of what's in front of it, but it has many pixels, so it can actually show you an image, a thermal image of what's in front of you. If you go into open air and image, for example, this room, you'll see all the hot spots where all the people are, and then everything else is cool. But if you put a plate of glass in front of it, and I think it's basically the same for pretty much all glasses except for exotic ones, research kind of glasses, that glass, first off, it's black in the infrared, so you will not see beyond the glass. But what you actually see is both the thermal radiation from the glass and the 4% reflection from the front surface of whatever's in front of the glass. And you're used to this from looking out a window. You look out a window and you see mostly outside, and you also see 4% reflection off the front surface of you and other things in the room. You also see 4% off the back surface, but that's not part of the story. So there's going to be the temperature. You will see thermal radiation coming from the window, and superposed on that will be thermal radiation reflected off the window from everybody on this side of the window. And that thermal radiation could be significantly bright, even though it's only 4% of your thermal radiation. Because you're warmer, you emit more thermal radiation, and that may, you may see it pretty clearly, even though it's just 4% of your thermal radiation. Does that fit with your experience? This brings up an issue that the thermal radiation that's emitted by a surface depends on its, first of all, it depends on its temperature. I've done that. Its temperature and its color. And its color at the its color in the vicinity of the thermal radiation wavelengths. The third thing, okay, so that's the story, but I wanted, is this here, yes. The power that surface emits in its own spectrum depends on a couple things. It depends on emissivity, which is the fancy word for where along the color spectrum it is between black, which is the perfect absorber emitter of thermal radiation, and is given an emissivity of 1. Or one of these terrible emitters or absorbers of thermal radiation, namely shiny, white, or transparent. Those are zeros. So emissivity is a measure that goes from 0 to 1, 0 being terrible at doing thermal radiation, and 1 being perfect at doing it. So that's emissivity. There's a constant of nature known as the Stefan-Boltzmann Constant, which is, it is what it is. The surface area, which is how much surface there is that's hot emitting thermal radiation, the more thermal radiation there is. And the last thing is temperature. It's temperature measured on an absolute scale, where 0 is the real 0, absolute 0. And it's temperature to the 4th power. Why the 4th power? Oh, that's a very high power of something for things in physics. The reason it's where does thermal radiation come from? It comes from the thermal motion of charged particles in the surface. As the atoms and molecules and pieces of atoms and molecules and charged particles are jiggling around because of thermal energy, they're charged particles that are shaking back and forth. They're accelerating. And an accelerating charged particle emits an electromagnetic wave. So that's the origin of it. That's how you emit radio waves. You put charged particles up and down an antenna. Woo, 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 woo. The accelerating charged particle emits an electromagnetic wave. It's beyond the scope of this part of the class, so this semester's class, but the jostling motion is key to emitting thermal radiation. And the more vigorous that jostling motion is, the more intense the thermal radiation becomes, because the charged particles are just getting to be better broadcasters of electromagnetic waves. So anyway, the temperature, the emitted power goes as the 4th power of temperature. It means relatively modest increases in temperature greatly brighten the thermal radiation coming off the surface. So you get situations like where you, being warmer than a window, are looking at superposed the thermal radiation from the window and the thermal radiation reflected of you. And yours dominates because you're warmer and you're just a brighter source of thermal radiation, and you overwhelm the window. A more familiar example, I mean, I should certainly point out that thermal radiation coming off the hot wood stove is intense. That's what you feel when you just stand there next to the wood stove. You're not touching it, so there's no significant conduction of heat. You're not above it, so there's no significant convection of heat to you. But yet you feel really warm. And if you put your hands in front of it, you stop feeling so warm. You're being bathed in thermal radiation coming off that wood stove. It's not visible, because the wood stove is just not that hot. But it's an intense stream of thermal radiation coming at you. It's hotter, you're colder, heat comes to you. So far, so good? When you open the freezer, my last thoughts, when you open the freezer and stand there trying to decide which flavor of ice cream to pull out, you're not touching the cold air, so there's no conduction of heat from you to the air. The cold air is undergoing convection, but it goes down. It cools and it descends to the floor, so it's cooling your feet. But you feel cold as you stand there in front of the refrigerator. What's happening is you're beaming, you're setting your thermal radiation at the freezer like crazy because you're hot. And it, because it's cold, is sending back very little thermal radiation. So it's basically a black hole for thermal radiation. The thermal radiation goes off you and doesn't come back at you, and you feel cold because you're just losing heat like crazy. All right, we'll stop. Have a fun weekend, and see you on Monday.